This week's Lab 9 talks about torque and equilibrium. And torque is a force's tendency to cause rotation of a rigid body. And torque is a vector, and the direction of torque depends on the direction of the force on the axis. So in these experiments, we will see which sides has greater torque or have equal. And the greater the lean of the balance beam, then the greater the difference in torques. And so for activity 1, I just kind of highlighted some things, some key points. And torque equals force times distance. So for activity 1, I would place a 10 kilogram brick on both sides, each 1 meter. So that would look basically like this: 1 kilogram, 10 kilograms on each side. And these, they would balance off. So that would mean that the torques are equal. So on to the next page. This one says to do our own experiment, and we would have to observe whether the change in the independent variable causes a significant change in the dependent variable. And the independent variable would be the different masses on the balance beam, and the dependent variable would be the changes in torque. And control variables are basically the same throughout each experiment that I'll do tonight. And that would be the type of brick, the length of the seesaw on both sides, and the gravitational pull. Even though when I say the length on each side of the seesaw, like each side has 2 meters, and like I know for one of them it asks about the change of the center, but for the first activity both sides are equal, and so that's why I said that the lengths on the seesaws would be equal. So for the first one, I did 5 kilograms. 5 kilograms would be placed on the left side. So I'll put 5 at 1, and then I would put 20 at 0.25. And basically those would balance out because torque equals mass times distance. So the mass would be 5 times 1, which would be 5, and then 20 times 0.25 would also be 5. And that's basically what it talks about in the first one. And you can observe that, you know, both of them are equal in torque. Okay. And to conclude, although the masses vary, the mass and distance is directly proportional to find which side has more torque. So even if I would put this right here to 0.25, this side would go lower, which would mean it would have more torque, which means that the mass is greater, and also there's a greater difference in the distance between the two. And so that's basically what goes on in the first activity. And so moving on to activity 2, it says perform an experiment to test if changing the distance between a force and the center of the beam affects the amount of torque. And basically the independent and dependent variables will be the same. And for this activity, I use the same masses. So being that the beam is balanced, the torques are equal. So then you can move the center of the beam to 0.5 on the side where 5 kilograms is. And this would cause the beam to lean to the right because the mass would be greater, but it would also have a greater distance. And what I mean by greater distance, I just mean a greater change in distance from having it at 0.25 meters. And then you can observe that the beam leaning down with 20 kilograms would have greater torque. And you can see this because 5 kilograms times 5 meters would be 2.5, and 20 kilograms times 0.75 would be 15. So change the center of a balance beam affects the amount of torque. And so same thing, torque equals mass times distance. So changing the center, you'd also have to match the mass and distances to go hand in hand with each other to balance it back out. So for an example, okay, so if I move this one to 2, I can move, and then look, it would balance out. That's because 5 times 2 would be 10, and 20 times 0.5 would be 10. So okay, another example would be if I put 15 to, let's see, to 2. So then you can, you know that 15 times 2 would be 30. So then you can put 20 at 1. And then you could also add a 10 to point, no. You would add, let me see, that would be 20. And then you could add another 20, 2.5. And you see, that's when they would balance out. Even though this side has more mass, they are equal because the distance is greater in this 15 rather than in these two right here. And that's basically what it is right here. Even though we can't directly move the sensor, you can always use different examples to figure it out. And then activity 3 is basically predicting where it would be. So this is kind of just touching off of both experiments. So suppose you have a 20 kilogram brick that's located, and I did this example without knowing that it was done up here. I would have used different numbers if I would have known, but all I did was do 20 times 0.25, which is 5, and then I did 5 divided by 5, and I got 1 meter right here. And then it says predict the distance between 5 kilogram bricks in the center, and that would be 1 meter. And then going to these practice problems, it says suppose you have a balance beam that is heavier at one end than the other. Where do you expect the center of mass on the balance to be? And then it says devise an experiment to find the center. So to conclude, all I did was, used knowledge of torque to figure this out. So the center of the beam would be closer to the heavier mass, which would then create the side of the smaller mass. It would be the same, but the torque would also be equal, being that the center would be greater to the heavier side with the mass. And then this would be an example of number 1. As you can see, 5 kilograms would be at 1 mass. Well, it would be at 1 meter. And then 10 kilograms would be at 1.25 meters. But this side would be greater. So then you would have to move this 10 kilograms a little closer to equal out this 5 kilograms. And that's how I did number 1. And then number 2 says a balance beam is hanging from a clamp located at the center of mass in the center of the balance beam. A 10-gram mass is hanging at the 10 centimeter mark, while an unknown mass is hanging at 58 centimeter mark. What is the mass of the unknown? So I came down here and I drew it out. And then basically to find the torque, you do 10 centimeters, which would be the distance, times 10 grams, which would be the mass, and you get 1,000. And then to find the unknown, you do 1,000 divided by 58, and you would get 17.2 grams, which would then balance these out. And then for number 3, it asks a 50 kilogram child is on one end of a 10 meter long seesaw. Assuming that the seesaw is provided in the center, how far from the center would a 70 kilogram child have to sit to balance it out? So I did 50 times 10, which would give you 500. And then I did 500 divided by 70 kilograms, which would then give you 7.14 meters. And that's where the 70 kilogram child would have to sit to balance out the 50 kilogram child. So that's basically how you find torque, and they are directly proportional with each other. And that's basically what Lab 9 talks about.